Hello students, and welcome to another video. I'm your teacher, Mr. Flint, and today we're going to be talking about empirical and molecular formulas. So we're going to do these together. The empirical formula is the lowest whole number ratio of a given compound or molecule. So for example, if I have hydrogen peroxide, H2O2, right, I can actually simplify this to a 1-to-1 ratio of H's and O's. See how I did that? Basically, like, it's just two of these, right? So you're seeing this is the empirical formula, right? This is empirical. And this would be what we call the molecular, right? This is what we're actually seeing out in the world. But when we do the math, it comes out that it's a 1-to-1 ratio of O's and H's. And we have to do some further calculating in order to know what our molecular formula is, which we'll do in part 2. But when you're calculating a given known percentage of oxygen and hydrogen example in this first problem, we can calculate the empirical formula for this, okay? But does it mean that it's the molecular? No, that's actually other information that's given to you. So we'll calculate that afterwards with a different problem. But for this first problem, when we're working with percentages of oxygen and hydrogen, I want to know, all right, what's my ratio of oxygens to hydrogens, right? Because if it's 94% oxygen and 6% hydrogen, well, is it a 1-to-1? Is it a 1-to-2 to 1-to-3, right? Is there, for example, H2O, like is there 2 hydrogens for every 1 oxygen? I don't know. I don't know if it's 2 hydrogens to 1 oxygen or 1 hydrogen to 1 oxygen, okay? But it does make sense that a lot of the weight comes from oxygen because oxygen's much bigger and it's much heavier than hydrogen is. It takes up more space, it has more mass. Okay? So when we calculate this, we want to suppose, all right, that we're working with 1 mole of everything. Okay, that's kind of our general how would I say it? I guess when we're working with problems, we always want to assume that we're working with just a mole of it, okay, just for the sake of just doing calculation, okay? So what we're going to do is we're going to pretend that we have 94 and 6. You see what they add up to? They add up to 100%, right? So if we have 100 grams of something, okay, we can imagine that 94 of those grams are going to be oxygen. So on this side, I'm going to write 94 grams of oxygen, and then we're going to have 6 grams of hydrogen. Do you see how I did that, right? Because 94 plus 6 is equal to 100. And let's just say that we have 100 grams of this sample. Well, 94 of it's going to be oxygen, and the other 6 grams is going to be hydrogen. Now we can make a comparison with our molar mass. So what we're going to do is we're going to multiply this by our 1 mole of oxygen, and that is equal to 16.00 grams of oxygen. Right, because our grams of oxygen cancel, and now we're left with moles. We're just converting our grams into moles. You can almost imagine this as our picket fence right here, and we're drawing our picket fence here like this. All right, and I'll set the next one up like a picket fence. And we're going to do a multiplication. We're going to convert it into moles. So 6 grams of hydrogen is equal to 1 mole of hydrogen. Sorry, we want to convert this, is equal to 1.008 grams of hydrogen, and that also cancels. So now we're going to have something called a mole ratio. So let me just punch this in my calculator. So we have 94 divided by 16, and that gives me a total of we'll just do 5.9, or 5.9, yep, 5.9 moles of oxygen. And then down below, I'm going to do 6 divided by 1.008, and that gives me rounding up 5.95, it's basically 6.0 moles of hydrogen. And what we're going to do now is we're going to divide by the lowest number, okay? And in this number, it's 5.9. So this one is going to be equal to 1, because 5.9 divided by 5.9 is 1, right? And so what I'm going to do is divide by 5.9, okay, moles of oxygen. And that tells me that our ratio is going to be 6.0 divided by 5.9. It's obvious that it's almost 1, but I just want to type it out for you. And that equals 1.01. So I'm just going to round it to the nearest whole number, and that's going to be equal to 1. So what it's going on here is this is a 1-to-1 ratio of oxygens to hydrogens. It's a 1-to-1 ratio of that balance. And what would happen if I had something like 6 and this was 12? Well, you can kind of assume that we're probably going to have 2 hydrogens for every 1 oxygen. Okay? So what you need to do is you divide them. And if it comes out as a 1 and a 3, it's a 3-to-1 ratio. Okay? But what happens if you get something like, I don't know, 1 and 2.5? Well, you can't work with a half. You have to have a whole. So we'll have to multiply the whole thing by 2. So we're going to have 2 of something for every 5 of something. Okay? And if you're having trouble with this, come talk to me and I can help work out a problem with you. It is in your, there is a practice problem that's like this. All right? But it has to be the grade, it has to be a whole number, like 1-to-1. It can't be 1 to like 2.5. So you have to go up to where you have whole numbers, which double it, which would be 2 to 2.5. Okay? But all we're doing is we're making a comparison saying how many oxygens are there to hydrogens. We're not finding the molecular formula, we're finding the empirical formula. We're trying to find out, is there 1 H or 2 H's? Is there 1 oxygen or 2 oxygens, etc. Okay? And we're finding that balance ratio. So in this example, it's OH. Okay? And down below, we're going to find and calculate a problem for molecular formulas. And this is a lot simpler than calculating the empirical formula because all you got to do is divide. Okay? So in this problem, the empirical formula is CH2O. That is our base unit. Okay? And we have to calculate the molar mass, and we're going to compare it to our actual given mass. All right? So the molar mass of CH2O, okay, the molar mass of carbon is 12.01 plus hydrogen, I'm going to put in parentheses, 1.008 times that by 2, and then we're going to add 16, because that's our molar mass, right? 12, 1, 1, and 16. I add that together, and I get 30. This is equal to 30.03 grams of grams per mole of CH2O. All right, so now what we're going to do is we're going to compare it to the given molar mass that we have here. So we're going to divide it, this number, by, or no, hold on, do that back. Oof, sorry, slow down. I have 150.05 grams per mole. I do not know what its formula is, but this is how much it weighs. But I do know that the base unit is this CH2O, and that's equal to 30.03. So I'm going to divide this by 30.03 grams per mole. And you'll notice that our units completely cancel on each other here. Okay? And we just do basically 150 divided by 30.3. And that gives me basically 5. This is equal to about 5. So this is 5 times this. So what I'm going to do with this base unit is multiply it kind of by 5. So it's going to be C5H10O5. Do you see how I did that? Right? Because I found in another problem, okay, I found that this given molar mass of this quantity, but when we did the empirical finding, we found that the base unit is CH2O. But then now we need to find out, well, what is it really? Is it glucose? Is it C6H12O6? Is it C4H, let's just say 8O4? Like, is it this one? Is it this one? I don't know what it is. But we do know what its molar mass is, so we can actually find what the correct number is. So all we've got to do is just divide it. It's pretty easy, actually. You just take the given known value and divide it by the molar mass of this, and then you just multiply that formula by the number that you find. So if it's 150 divided by 30, that's 5 times that. Okay? All right, so you have to calculate the empirical formula before you can calculate the molecular formula. So the correct answer is C5H10O5. Okay? All right. This can be kind of tricky. This just takes practice, right? So you got to find this empirical formula, what's its base unit, and then you can calculate what its actual molecular formula is, what it is actually in what we're working with in the lab, okay? Because they're not always going to be CH2O, right? It's going to be something of a combination of that, multiples that are much larger than that. Okay? Thanks again for watching. Until next time.